Hi again. We're going to look at section 4.2. It's an example of a discrete random probability distribution that's pretty common, a binomial distribution. And so we're going to take a look at what makes a binomial experiment. The experiment is repeated for a fixed number of trials, and each trial is independent of the other trials. There are only two possible outcomes of interest for each trial, and you can classify them as a success or a failure. The probability of a success is the same for each trial, and the random variable counts the number of successful trials. So, for example, I'm sorry guys, don't get mad, but if we let X be the number of girls born to a family with 5 kids. Okay, then a success is being a girl. And the probability of a success would be 1/2. And X can be what values? You could have no girls, 1 girl, 2 girls, 3, 4, or 5. Those are the only possible values for X. Okay, and then anything else would be a failure. So you're either a girl or a failure. Are you catching on to this? I'm just kidding. Now you can make just about anything a binomial experiment, but it has to follow these rules. So once again, fixed number of trials, independent, success or failure, probability of success is the same, and the random variable counts the number of successful trials. Okay. So it's just another example of a discrete distribution. We have some notation here. N is the number of times a trial is repeated. So in that last example, N would be 5, because we were looking at 5 kids. P is the probability of success. Q is the probability of a failure. And I think we've looked at this before when we look at complements, but Q is 1 minus P. And then X is the count, so we're looking at from 0 to N. So decide if the following is a binomial experiment, and if so, list the characters. So the characters are N, P, Q, and X, okay? A certain surgical procedure has an 85% chance of success. The doctor performs it on 8 patients. The random variable counts the number of successes. So X would equal the number of successful surgeries, and the probability of a success would be P, which is 0.85. So Q would be 1 minus that. So Q is 0.15. And then who else do we need to look at? What's N? In this case, N is 8. Now, is this binomial? Well, does it meet the criteria? Well, we assume that each surgery is independent of the others. I guess they wouldn't be if he did 8 surgeries in a row, because the last one he'd be exhausted, but we'll pretend that we assume that. They're all independent. It's a fixed number. You're either a success or a failure. I think we're in pretty good shape. Oh my gosh, we got it right. Okay. And then X is 0 through 8. All right, awesome. Okay, how about this one? Is this a binomial experiment? We've got a jar that has 5 red marbles, 9 blue ones, and 6 green ones. You randomly select 3 marbles, but without replacement. And then the random variable represents the number of red marbles. So, yes, you have a fixed number. Yes, you have what? A count. And you have a success. You're either red or you're not red. Okay? But the without replacement makes it what? Dependent. And so since it's dependent, it fails. Boo. All right. We got it right again. Okay, now this formula is miserable, so this is really why I'm doing this. The binomial probability formula, I want to point out that this piece of the formula right here, this notation, your calculator can do for you if you'd like to figure out how. But it matches this. So this notation means how many different ways is there to combine X things out of N total things. Okay, And then P is your probability of success, and Q is your probability of failure. And this is how you calculate binomial probabilities. And a lot of times binomial probabilities is abbreviated like this. So what's the probability that binomial experiment would be this? I'm looking at 5 kids. The probability of success is 0.5. And what's the probability that I would have exactly 2 girls? Okay, so we do n factorial, which that's an interesting, it's like n, like I'm excited about it, but n factorial, so 5 factorial over 5 minus 2 factorial times 2 factorial, and then the probability of a success is a half, and we're looking for 2 successes. Probability of a failure in this case is a half, and we're looking at 3 failures. So the exponents here should always add up to n. Now, what does this factorial button mean? 5 times 4 times 3 times 2 times 1. And then this is 3 factorial, so it's 3 times 2 times 1. And then 2 factorial is 2 times 1. So then over here we end up with 1/2 to the 5th power, and we just need to clean some of this up here. So like the 3, 2, 1 would cancel the 3, 2, 1. 2 would divide into 20 10 times. So now we just need to do 10 times 1/2 to the 5th, or 10 over 32, or you can change that to a decimal. And there you get your probabilities. Now, I'm also going to show you how to do binomial probabilities on StatCrunch, and I'm also going to show you how to use the binomial table. The binomial table is found in your appendix, so we will take a look at that in a different video, but this will get you started with the pencil and paper part. So here we have the probability of a success on exactly 2 patients, and we're looking at 3 patients total. So this is similar to what you saw before. Probability of success is 0.75, N is 3. If P is 0.75, then Q is 0.25, and we want the probability that it's exactly 2. So we need n factorial over n minus x factorial, and then x factorial. Then the probability of a success raised to the number of successes you are interested in, and the probability of a failure raised to the number of failures. And remember that total should sum up to n. So this numerator is 6, because 3 times 2 times 1. The denominator is just 2. And then you need to actually use your calculator to finish out your work. But you can do this part before you get on the calculator typically. Now, they had you do it doing the tree diagram. That's honestly more of a pain in the butt than the formula I just used. So here you can see them showing the formula. Okay. The next few pages show you how to create a probability distribution using binomial probabilities, and so you have to use the formula to find all of these pieces here. But I'm going to do something similar in another video, so we'll come back to that. And so I'm going to stop our video here. Oh my goodness. But I do want to point out that this is exactly why you want to use your technology, because, for example, let me show you this one. They did the work for me. So 56% of adults like texting because it's quicker than calling, and we're given all of this information. So if I asked you what's the probability that X is greater than 5, that's the probability that X is 6 plus the probability that X is 7, right? This is just a for example. Now this, I am so sorry. This for example means I need to add these two numbers together. Okay, that's not so bad. But what if I wanted the probability that X is greater than or equal to 3? Now I got to add all of these together. Well, adding them together is not the big deal, but finding all of those is a pain. So that's one of the reasons to use our technology. So I'll show you that in another video. Have a great day.